Welcome. In this video, I am going to go over some regions of interest, which is abbreviated ROI, and classification techniques. This is introductory material to get you ready for exercise 7 from your Introduction to NV Lab manual. So when we think about contrast stretching, it's important to understand why do we do it. And the idea is that contrast stretching systematically expands the range of digital number values to the full limits as determined by the byte size in the digital data. So in our original image, we have digital numbers represented from 84 to 153. By stretching to the full capabilities in an 8-bit image, which is 0 to 255, we are enhancing our image, and the original file and the resultant file are shown up here. And you can see just visually the change is pretty dramatic, and we are able to use more digital numbers to get more information from our collected data. And Landsat is 8-bit data, and so that's why we are able to stretch to 0 to 255 digital numbers. Here is an example of a natural color image of Morro Bay, California. And if you wanted to explore further image processing and interpretation, there's a link here that you can explore for some background reading. As you know, there's no textbook required for this course, and you can get an introductory understanding from most of my lectures, but I occasionally will provide you with other resources if you're interested further. I would rather, for the purposes of this class, if you're busy, which most of us are, focus on moving forward with the assigned reading and with the lecture material, which is plenty of information for you. Okay, so this is our natural color image of Morro Bay, and we can see here band 3 represented in the right in shades of gray. So we know that that is a band that's collected within a certain portion of the electromagnetic spectrum, and we are seeing the digital numbers that are the distribution is shown here in this histogram of band 3. And so we're looking at values from about 9 to about 180, with the concentration of images being shown, pixels that are represented down here. And you can see this is a very, very tall category, and that makes sense because we have a very large swath of ocean, and ocean is going to register very low in terms of digital numbers, as we know, because it absorbs more energy than it reflects. So with contrast stretching, what we want to do is modify the range of light and dark tones or gray levels. And you can do this in a photograph or a computer display, and we're doing it with satellite data or rasters. And it is the single most informative and revealing operation performed on a scene. So just a review here. Here's our histogram, again, of what is available in that band that we're considering. So Idrisi's standard linear stretch program was applied to this image, and it's improved the quality of the image. As you can see over on the left, we have a very rough contrast between dark and light, and there aren't a lot of subtle details available to us because we aren't using all of the digital number capabilities. When we stretch this data, now we can see the ocean is very distinct from the surf zone, which is very bright. We have a sandy beach here, and we can indeed see mountain patterns and riverine dendritic patterns in this image on the right. So not changing the data per se, we are manipulating the data just so that we can get a better visual of what is represented in the data. So we can perform a linear stretch so that 9 goes down to 5 and the 65 is stretched to 255. So we might ask, well, why don't we stretch down to 0? Theoretically, there are very few pixels in an image that will be a pure 0. And the same thing, there's very few images that are a pure 255. There can be, I keep saying images, please excuse me. There are very few pixels that will be a pure 255. Now, there are some, and this stretching will be determined by the computer. It decides for you how much is reasonable to stretch your data. But again, the take-home message here is that when we compare the original scene with our stretched value, it's obvious that the scene features are now more discriminable. And the image is still looking rather dark. So if we notice that this histogram is indeed polymodal, which means that there are many areas that have definite spikes in the representation of pixels, which means there's a large concentration of pixels here, and there's a large concentration of pixels here. And the first one I showed you is a bright area of the image, and then the other one would be the darker ocean area of the image. But this stretch right here is showing very bright, and it is a representation of light tones in the image. If we use a linear with saturation stretch, we can get 5% of the pixels at each tail end of the histogram that are assigned to single values. So we're taking this mode, this spike in the frequency, and we're asking the computer to further distinguish those pixels into greater visibility and slightly different categories. Now, if we look at the results of our linear with saturation stretching, you can see we now have greater numbers of categories at both the low end of the digital numbers and the high end. So that very, very, very tall peak in the histogram at the bright end of the reflectance values of pixels is now broken up into many different representations. So a stretch that favorably expands some part of the digital number range at the expense of others by dividing the histogram into classes containing equal number of pixels. That is a wordy definition of linear with saturation stretching. So the idea is that if most of the radiance variation occurs in the lower range of brightness, those digital numbers may be selectively extended. And this is an example of extension with a greater proportion in the higher values and a finer detail and feature distinguishability in the image. Okay, so again, note that the frequencies are spread apart at the lower digital numbers and then the higher digital numbers. Most of the pixels in the middle don't change very much. So in the top plot A, we see the digital number values range from 60 to 158. And that is our histogram here in the top plot. In B below, there are now very few pixels that, again, from 60 to 158 that are represented. And now what we're doing, as indicated by these arrows, is we're stretching out the lower limits of the data to match the capabilities of the display in the computer. So when I say that we're not really changing the data has been collected and that doesn't change. That is static. What changes is our display on the computer screen of the representation of those pixels. And so you can see here that in the actual image, there weren't really any collected values less than 60, but our computer monitor can distinguish many different fine shades of gray. So you're stretching your data and you're asking it to display based on the full capability of the computer. And we can see here again, these arrows are showing you that spread out nature or the stretched capabilities that we can achieve. So now in plot C, the linear stretch involves moving the 60 value to 0 and the 158 value at the higher end down out to 255. And then all of the intermediate values are stretched proportionately. So there's no accounting of the pixel frequency distribution made in this stretch. So much of the gray level variation is applied to scarce and absent pixels with low and high digital numbers, and the resulting image doesn't always have the best contrast rendition. So in plot D, we're looking at pixel frequency considered in assigning the stretch values. So it's taking into account the distribution or the frequency that is shown in our data collection. It's honoring those areas where we had the most pixels collected. And so now we're giving a broad stretch from 38 to 255, and the values of 107 to 60 are spread differently. This is histogram equalization stretch. So again, this is looking at the natural or normal, if it is normal, distribution within our pixel values, and it is stretching them accordingly. It's more than just stretching out the values, it's looking at the statistical representation of the data that we collected, the data being those digital numbers in the image. Now, finally, in the bottom, we have a specific range, and infrequent values between 60 and 90 are independently stretched to bring out contrasting gray levels. And this would be something that you might want to do if you were interested in a very special or specific, I should say, could be special, portion of your image. And so if you know as an analyst that 60 to 92, let's say, represents wetlands, and you really want to look at this image for wetland features, that's where you might apply your stretch. And so this is showing you that the image is going to stretch just that portion of um, the pixels. Okay, you're going to work with scatter plots, and let's start by looking at what a scatter plot is. In Envy, you're going to display two bands. Here's band 1 and band 2, and you're going to display them in a Cartesian plot. And this is what a Cartesian plot is. And so this provides a comparison of the x and the y coordinates. And if neither band contains dependent data, then either band can be plotted on either axis. And the scatter plot illustrates the degree of correlation between the two bands. So if you want to know more, you can certainly Google the statistics of a correlation. But briefly, correlation has to do with the representation between your x and y variables. A one-on-one correlation would be just a completely straight line. And that means that every pixel in this band, if it were the same as every pixel in this band, they would plot out equally as a straight line. So you can see here that the relationship does seem to show a pretty strong positive correlation or upward trend. You're also going to look at dancing pixels, which is pretty fun to play with, I think, in NB. And it takes a 10 by 10 pixel area surrounding your cursor location, and the dancing pixels are clustered together and have a combination of spectral values that corresponds to the area around the cursor in the image. And so you can use your dancing pixel in order to see how groupings of pixels are behaving. You can also look at areas where the pixels are not clustered together, and that's going to be indicative of transition zones. It's going to be indicative of mixed pixels, and that tells you if you have pixels that are very spread out, like you see here in this portion of your scatter plot, it means that you're probably likely looking at an area with mixed pixels. And so edges of urban areas, even within urban areas, you can have very strong mixed pixels. If you have a very bright, large white roof next to a parking lot, which is dark asphalt, that's definitely a mixed pixel. Edges of buildings provide mixed pixels, edges of recreation areas, water within a very vegetated area Those are some examples of mixed pixels that you might see. You're going to be looking at density slice again in terms of a data cloud. In this representation, the clusters of pixels or arms protruding from the center and corners are unique features on the ground. And then the center here is showing you cloud pixels that contain a mixture of materials. And so if we are blocking out the different classes according to color, these areas here showing different colors are areas where there are mixed pixels. And so you can see that there are some stripes of yellow intermixed with the green here. Here's where we have some mixed areas of blue and purple. And again, in the center of the cloud, you're going to find mixtures of materials. Um, the warmer colors are thicker data distribution, and warm being your yellows, reds, and oranges down here. And your cooler colors are showing thinner data distribution, the cool being the blues and purples. A region of interest is an area that is contained and separated out for analysis purposes. Here's an example of a plot made in Envy, looking at a region of interest from this image that you see here. And you're going to combine a scatter plot, which we've already covered, with these types of plots in order to analyze your data. And so you're seeing here, here are the statistics for that region of interest, and it's showing you for the region of interest that was selected, these are the values for band 1 with a minimum of 77 to 177 pixel value. And in contrast, let's jump into one that shows a lower minimum. Band 4 is 37 to 251. So that means that this region of interest displays pixel distributions according to individual bands with these values. If, for instance, you wanted to look for a band that is showing you a particular mean, and you would need to know again how that information was collected, and that's your engineering specs of your satellite, which is very easy to Google, and I've provided some information for you in this week's module on the Landsat 8 specifications. So knowing that each band collects within a certain range of the electromagnetic spectrum, you can then look and see how is your region of interest behaving according to that particular wavelength. Okay, so again, each of these lines that you see drawn in this plot are showing you different band representations, and then your data is displayed below. All right, stepping back from the tools, and let's talk about the theory of what we're actually doing with classification. Two main types, unsupervised and supervised classification. The main distinction is that unsupervised, the computer is running the show. Algorithms are automatically grouping pixels that have similar spectral characteristics. And when we say spectral characteristics, we're talking about means, standard deviations, covariance matrices, and correlation matrices of our digital numbers. Input here is shown by different numbers in different bands for one image. The algorithm says, I am going to put all of these pixels that you see as B into the B spectral class, and we have an A spectral class and a C spectral class. As an analyst, we can then go in and say, well, A is water, B is agriculture, and C is rock. So you are going to combine not only what the computer tells you, but you will be doing visual inspection as well. The computer's just going to put things into groupings based on spectral similarity. You as an analyst will need to go in and define what that is. And so you can use Google Images, and you can use the actual band images. You can see features in that. And we know it's very easy to tell the difference between water and agriculture and rock. As you get more sophisticated in your GIS use, you might be looking at the difference between healthy trees and dead trees of the same species. This is a very common application of remote sensing with the pine beetle infestation problem in the Pacific Northwest, because the dead or dying trees have a different spectral signature and they tend to be located in clumped areas within many, many acres of tree stands. And so you can identify which areas of a scene have dead or dying trees. That's a little bit more sophisticated than the difference between water and agriculture. Going back to the second type of supervised classification, now you're using what is known as a priori information, and this is a combination of fieldwork, map analysis, and personal experience. You are assigning the training classes. You are drawing areas or regions of interest, and you're saying these areas should be classified together. And you can have too many areas and too much information. You can also have too few areas. Urban tends to be a wide range of digital numbers. In contrast, snow or water tend to have a very narrow range of digital numbers at opposite ends of the spectrum, but snow is very reflective and bright, and water is very absorptive and dark. Here's our same example of water, um, agriculture, and rock. And you can see here that these are the representative training classes that the analyst drew on our representative raster. And then the analysis by the computer is a little bit more sophisticated than you can see unsupervised. So unsupervised attempt will identify spectrally homogeneous clusters of pixels within the image. That means that they have similar digital numbers. If the results of spectral groupings have an unclear meaning, from the user's point of view, you can then go in and do supervised classification. Now, in fact, supervised classification is what you're going to do most as an analyst, unless you're starting a project and you don't know much about the area and you need to get a baseline or a launching place for your further investigation. Once you establish the spectral groupings, the analyst will associate an information class with each group. The unsupervised approach is often referred to as clustering and results in statistics that are for spectral statistical clusters. Here is a scattergram showing you unsupervised classification. The plus signs that you see in the scattergram represent the mean or central points of each class, and the circles or ovals are drawn around all of the pixels that are contained within that individual class. And so we can see that the biggest class with the most variation would be this red oval here. And then we have smaller clusters or classes of pixels that are represented by those smaller ovals and or circles. Envy's simplest classification method is a clustering routine, and it's unsupervised either isodata or k-means classifier. The advantages of unsupervised: you don't need previous knowledge about the scene. You can use information from the image to identify the spectral clusters interpreted as classes, and the user can specify the number of classes. So the way that it works in an abstract sense based on the algorithm is that you have, let's say here, a comparison of band 3 and band 4 from the same scene or area in your satellite imagery data. Now, these dots here are representing where the means would be if band 3 and band 4 represented the same digital number. Now, we know that that doesn't happen. There are no natural areas that are going to show an exact linear correlation between two different bands in an image, but this is where we start. And we're showing a distribution of brightness values according to this gray area that is drawn of this data. These curves that you see along your X and Y axis are representing distribution. With this is the Greek letter for mu. It represents the mean center, or the mean of your data, which is like an average, but it's a little bit different. It's your mean. And then we have standard deviations going down our normal distribution curve. Here's -1 standard distribution and +1 standard distribution. Notice that if we're considering our data here on our x-axis, it's showing that most of our data will fall between -1 and +1 standard deviations. All of our data falls within 3 standard deviations on either side of our mean. If you want more statistics, you can jump into it, but I'm hoping that that gives you some interpretive background for what we're seeing here. Okay, so this is the theorized situation, which we know doesn't really happen. When you apply your unsupervised ISO data classification, now the computer is saying we're going to put this data into clusters that are more meaningful than a one-on-one relationship. And so now we have the data here. It's saying that all of the data in this ellipse is more similar to each other than in this ellipse next to it. Okay, so then the same idea would apply, that the data in this ellipse are more similar to each other than either of these ellipses next to it. Okay, doing more iterations, looking at our second iteration here in C, we're now seeing that these ellipses are starting to show a different shape. And that's because the data is clustering out more and more away from a one-on-one relationship, which doesn't exist. And then finally, this is showing you nth iterations. You have a lot of power in your computer, and you can run multiple analysis on your data. And now we see a very, very different relationship than the one-on-one, with the centers. Notice the centers and also the shapes of our ellipses have changed. And now we can be more confident in example D than we were in example B, of everything that is assigned to this class is more similar and more alike each other than all of the pixels that are assigned to this class. Let this sink in for a moment. It's just a very abstract way of showing you how these classes are formed with algorithms. Okay, so user specifies a range of output classes. The one we just looked at was 5. And for general, looking at an area, you might only want to use 5 classes. There are some examples where it's appropriate to use 2 classes. So more classes doesn't mean better science. If you were looking at the shrinking of the Aral Sea, and that is a freshwater body of water that is located, it's completely landlocked and inland. Now, the Aral Sea is shrinking and it is evaporating. And so if you wanted to compare the size of the Aral Sea in a 10-year period, you could run 2 classes and ask the computer to show you water or non-water. It's very valid and it's very powerful. You're not interested in the vegetation around the Aral Sea. You're interested in the volume of water and the change in the volume of that water. So you could do just fine with water versus non-water. Now, if you're looking at suitable habitat for a population of endangered wolves, you're probably not going to just use 2 classes. You're going to use multiple classes in order to distinguish where that suitable habitat is located. All right, Envy uses iterative class splitting, which we looked at. It merges and deletes pixels to determine the final number of classes. With unsupervised k-means classifier, it calculates initial class means that are evenly distributed in data space, and it iteratively clusters them using a maximum distance technique, saying we have a center of these pixels, and we're going to include all pixels within a minimum distance of that pixel center. I think I just said maximum. I apologize. It's minimum. And it classifies means and reclassifies the pixels with respect to new means. All pixels are classified to the nearest class unless a standard deviation or distance threshold is specified. In that case, the pixels may be unclassified if they do not meet a selected criteria, and this process will continue until all pixels have been assigned. And I'm going to bear with me a moment. I'm going to go back and show you. This would be the minimum distance. So if a pixel is going to be classified in this final grouping here, it has to be this much distance away from what our mean values would be in both bands 3 and 4. If there was more variation in either of those bands, that pixel would not fit in this class. Okay, bear with me. I'm going to jump forward. Now, we're going to switch gears here and talk about supervised classification. In the real world, you will use both, mostly supervised classification. This is where you assign samples of known identity. The pixels are already assigned to informational classes, and then you classify unknown pixels to match that classification. This assigns unclassified pixels to one of several information classes. So supervised classification, in looking at this procedure, the image analyst supervises the pixel categorization process by specifying to the computer algorithm numerical descriptors of the various land cover types present in the scene. Representative sample types of known cover types called training areas or training sites are used to compile a numerical interpretation key, and this describes the special attributes of each feature type of interest. So each pixel in their data set is compared numerically to the categories that have been created, and they are either classified as belonging in that classification or not. And then the final result is a thematic map where each pixel has a fixed label or class assigned to it. All right. I am going to show you an example from Envy, and I'm going to show you an example that I worked on in the real world. So if we look at creating training classes, combining fieldwork, map analysis, GIS or reference layer, and personal experience, meaning you can actually get your boots on the ground and sample what these different types of fields are. Looking at maps, if we have knowledge of what those fields will look like from a satellite image, we can classify them as alfalfa, cotton, grass, or fallow. We can use a known GIS or reference layer, oftentimes, especially with wild areas and wild classification, there are already reference layers that exist, and that's where I'm going to show you an example of a project I worked on. And then personal experience, you may know your study area. All right, pardon me for a moment. I'm going to back up, and I'm going to shift gears. Okay, I wanted to jump in and do a little bit of a side note here and show you some products that are available as a collaboration between Google Earth, National Geographic, and ESRI. So I was very privileged to work on this project as a National Geographic explorer, and I worked as a mapping expert identifying areas of the world. My assigned biomes were mangroves, and I looked at satellite images from several areas of the world, and I helped to create training classes that ultimately led to part of a national world atlas of um, different types of land cover classes, and it is housed on the ESRI site, and it is now available as a layer that you can use in mapping. And so again, this is based on the work of dozens of analysts and it is a classification of all of the different land cover globally. And we created those algorithms and the training classes. I should say we created the training classes that the computer then used in an algorithm in order to break up the world into different types of land cover. And this is a global coverage, and I'm going to zoom in here a little bit, and you can see that as you zoom in, it actually can get to some pretty good detail of what is being represented on the ground. So here is an area on the East Coast, and it's showing a wetland area next to some land cover. And again, very easy to distinguish that water feature class from um, the surrounding areas. Okay, and here is our legend here that is showing you the different properties of that class. And then if we go in and we look at some other possibilities for us, I'm going to back up here and I'm going to go back to my search, and here is a little bit of metadata about 5 billion hand-labeled Sentinel-2 pixels were sampled from 20,000 sites and distributed across all major biomes of the world. And I was responsible for what seems like a good portion of that 5 billion pixel designation, but there were many of us that were working on this project. And so this is something that you can use in your own GIS work. And again, there's several different representations of this project, and I will let you explore that on your own. For now, let's go ahead and return to our coverage of the process of supervised classification. So we just looked at some training classes that were created for global data set, and let's sum up with some details what happens behind the scenes with supervised classification, I should say. Sorry, my brain is excited about that National Geographic project. It was a really great project, and that's I'm proud of my involvement, but it's a big move forward to have a global data set. That was the the big move forward for conservation and ecology, and looking at things like studying landmass and biomass of trees. And the United Nations is using it to estimate carbon flux and also food production possibilities. It's a pretty important global project, and I was a very small player in it, but it was exciting to see it unfold. Okay, with supervised classification, this is a parallel piped classification. The computer takes into account variance in training classes. You can get a problem with a lot of overlap, because when you are looking at variance between hay and fallow, there are variance classes, which means deviation from the mean, and this area that you see right here with H and F in both um, represented in this small little rectangle here, it means that there's overlap. There's also overlap possible in other classes. So in this classifier, multi-dimensional boxes are constructed for each class. It uses class mean and standard deviation, and the pixels are tested against each other to determine its membership. This is a visual of that minimum distance, and so if we have our mean here represented by the dot, you can see the clusters of pixels of wheat and hay and the different other fields that we saw earlier in this presentation. And so they all have a mean, which is represented by this plus sign that you can see. It doesn't stand out all that well, but here's a good example of a plus sign. And then the distance to the mean of all of the band capabilities or pixel capabilities within those bands. And so distance from a universal mean is used as a categorizing factor for putting pixels into similar spectral classes, which then translate into similar types of ground cover, in this case, the similar types of fields. So in this classifier, the pixel is allocated to the class for which it has the closest mean. Now with maximum likelihood, now we're looking at a Gaussian classifier, and it is looking at covariance and more sophisticated statistical analysis. So with the variance and covariance of these training class pixels, we're assuming a normal distribution and we're putting things into categories. It is the same idea as minimum distance, but it's more sophisticated, not looking at the actual values and how far away they are from a mean, but now we're looking at the statistical probability of that mean, and that is variance and covariance. Okay. Again, very similar types of raster products are produced, but maximum likelihood is looking at distributions. And now we're factoring not just distance, but we're also factoring what is shown here as a Y feature as probability. Not just the distance in the digital numbers, which would be the comparison of X and Y axes. Now we have a third dimension. So of course it's going to be more sophisticated. And we're looking at multi-dimensional space. And these are the peaks of corn, hay, forest, urban, and sand. And so you can see here that there is a apparent normal distribution of these features, and then the three-dimensionality is representing the classes where those pixels are being assigned to. With Mahalanobis distance, that is always hard for me to say. It always has been, is keep trying, but it's the Euclidean distance away from a center point, and Euclidean, it is based on a sphere or an ellipse, and the ellipse is generally longer than it is wide. It is rarely a perfect circle, but it can get to be close to a perfect circle, and not that circular is better than elliptical. I shouldn't say close. It can get similar to a circle, but mostly you will see these types of ellipses. And so the distance between each green point here and the center is different, and this is giving you Euclidean equidistant pink circles of classifications. Another type of supervised classification is binary encoding. This encodes the data and end member spectra into zeros and ones. And it's saying either it falls within a range of a spectrum mean or it doesn't. So that example that I talked about earlier of the RLC, and this is not the RLC, but it is definitely a water body. It might be useful for you to distinguish just between water and then non-water. And we can see down here in our resultant image, we have all of our water showing up as bright green pixels. You can compare classifications. This table is looking at the different types of classifications, and we have binary, and we have parallelepiped, minimum distance, Mahalanobis, and maximum likelihood that we considered in this lecture. And this is showing you the comparative summary of the results of those different types of classifications. The best one is going to be based on your field study and your research project. In summary, unsupervised versus supervised. In the unsupervised approach, the user first determines spectrally separable classes and then defines informational utility. And based on information categories and examining their spectral separability. So even though you're determining the final classes and labels, the computer is determining where those classes are going to fall out in the pixel distribution. So more control in supervised, but in unsupervised, you can perform this on an area where you don't have a lot of knowledge of the ground. So in areas of complex terrain, the unsupervised approach can be preferable to the supervised one. So the user may have difficulty in selecting training sites because of the variability of spectral response within each class. If you get a very strong salt and pepper effect in an image, you can appreciate that in terms of digital numbers. You can appreciate that drawing regions of interest around an area like that would be very complicated, and you're going to have a huge statistical uncertainty in areas that have small patches. For instance, areas that have near rivers, and there's a big distinction between a narrow band along the river and then the vegetation that spreads out away from the river. So in that case, unsupervised might work well for you. Also, a priori ground data collection can be very time consuming, and time and money are always factors on projects. Supervised approach is subjective, and you are assigning these classes and you're saying everything I see in this image is the same class. So again, you can have more statistical uncertainty, and you may make decisions that don't translate into real world distribution of the pixels. Unsupervised has a potential advantage of revealing discriminable classes that were unknown from previous work. So again, that patchiness, if you're looking especially at a stand of trees, if you are just doing supervised classification, all of the trees might come out to be in the same class, the live trees versus the dead trees. But if you do unsupervised, you might see some patches in your study area that you hadn't known about before. However, when definition of representative training area is possible and statistical and information classes show a close correspondence, the result of unsupervised classification will be superior to supervised. All right, thank you very much for your attention.